Hello everyone and welcome to our sixth lecture of the CS2100 Discrete Structures course. And in this part one of the lecture, we will introduce a new proof technique called proof by contradiction. So before we get to proof by contradiction, let's start by doing a couple of simple examples to practice proof by induction, which we introduced last time. Okay, so here's our first review problem. So we want to use induction to prove that for each integer n greater than or equal to 0, 6n plus 4 is divisible by 5. Okay, so if you remember our steps that we have to take to do a proof by induction, first we have to define what we are actually trying to prove. So our Pn is equivalent to 6n plus 4 is divisible by 5. Okay, now the next step is our base case that we have to prove. So for this problem, we want to prove this for every integer greater than or equal to 0, and so our base case is when n is equal to 0. So we have to show that 6 to the power of 0 plus 4 is divisible by 5, and so we get 1 plus 4, which is equal to 5, and 5 is divisible by 5. So we showed it for our base case. Now we assume our inductive hypothesis. So we assume that P of n holds. And we have our inductive step. And in our inductive step, we now want to prove that P of n plus 1 holds if we assume that P of n holds. So we want to prove P of n plus 1 holds. Okay, so what is P of n plus 1? Or actually, so P of n plus 1 is equivalent to 6 to the power of n plus 1 plus 4 is divisible by 5. So this is what we want to prove, and if you remember, we want to prove this by somehow plugging in this inductive hypothesis, which tells us that 6 to the power of n plus 4 is divisible by 5. So okay, so let's try to do this. So we have 6 to the power of n plus 1 plus 4. That's equal to 6 times 6 to the power of n plus 4. Okay, and that is equal to, so remember, we want to somehow plug in our inductive hypothesis because we know that this is divisible by 5. So we want to somehow get this form in here. So let's try to pull out 6. So we have 6 times 6 to the power of n plus 4. And then we have minus 20. So what I just wrote is equivalent to this previous expression. If you multiply it out, you can see that. We get 6 times 6 to the power of n, 6 times 24. 6 times 4 is 24, and minus 20 is plus 4. Okay? Okay, so from here, we can now plug in. We know that 6 to the power of n plus 4 is divisible by 5, which means that that is equal to some k times 5, where k is an element of z. That's from our hypothesis. And so if we plug this in, we get that this is equal to 6 times k times 5 minus 20. And that is then equal to 5 times 6 times k minus 4. And that is equal to 5 times L, where L is an element of Z. And that is because of closure of multiplication and negation. And so from here, we know that 6 to the power of n plus 4 is divisible by 5. And we prove this using induction. Okay. So given that induction is maybe the most important proof technique that we'll cover in this course, let's look at more review. Okay, so this is similar to what we've done before. So we want to use the induction to prove that for each n greater or equal to 1, this holds. So this is our B of n. Okay, so let's first do base case. Don't forget about base case. So that's when n is equal to 1. So we have sigma I is equal from 1 to 1 of I times I plus 1 and 1 over that has to be equal to 1 over 1 plus 1. So that's this right hand side. So on the left we have 1 over 1 times 1 plus 1 has to be equal to 1 over 2, and that is indeed the case. So we prove our base case. Then we have our hypothesis. So hypothesis is that sigma I is equal from 1 to n of 1 over I times I plus 1 is equal to n divided by a plus 1. And now, so we assume it for n. Now we have to do our inductive step. So we want to prove this for n plus 1. So let's see what sigma. So we want to prove that sigma I is equal from 1. We want to show that sigma of I is equal from 1 to n plus 1 of 1 divided by I times I plus 1 is equal to n plus 1 divided by n plus 1 plus 1. Okay, and we want to show this using our hypothesis. So we know how to do this when we have to deal with this sum sequences. So we want to express this sequence on the left recursively so we can plug in this hypothesis that we have. So how do we do this? So sigma I is equal to 1 n plus 1 of 1 over I times I plus 1 is equal to sorry, this should be sigma. Let me erase this. Is equal to sigma I is equal from 1 to n of 1 over I times I plus 1, and then plus, so we are missing the n plus first member. 1 over n plus first, so that's when I is n plus 1, n plus 1 times n plus 1 plus 1. Okay, great. So now this one here matches what we have on the left in our hypothesis, which means that we can plug in this right hand side in and leverage our hypothesis. How we get n over n plus 1 plus 1 over n plus 1 multiplies n plus 2. And now that is equal to, let's add these up. So we have n plus 1 times n plus 2, and above we have n times n plus 2 plus 1. That is equal to n squared plus 2n plus 1 divided by n plus 1 times n plus 2, and that is equal to n plus 1 squared divided by n plus 1 times n plus 2, and that is equal to, so these things cancel each other, is equal to n plus 1 divided by n plus 2. And that is what we were trying to show in the inductive step. So that concludes this proof by induction. Okay, so make sure to practice proofs by induction that include sums of sequences. Let's take a look at another problem by induction that we want to prove by induction. This will be our last review problem for this lecture. So we want to prove that the sequence defined by ak is equal to a of k minus 1 plus k plus 4, where a of 1 is 5, so this is a recursive sequence, is equivalent to p of k is equal to k times k plus 9 divided by 2. So that's a little bit similar to the previous problem. So what is our predicate? So p of n, or proposition that we want to prove, is equivalent to a of k is equal to p of k for k greater than or equal to 1. We know that because we have the base case here for this sequence. So first we show base case. So that's when n is equal to 1. Oh, sorry. I made a mistake in notation here. So this should be n, not k. Note that you can choose whichever letter we want, but it should match what we have here in the parentheses next to p. So we have a of n is equal to p of n for n greater or equal to 1. So base case when n is equal to 1, we want to show that, well, on one side we have a of 1 is equal to 5. On the other side we have p of 1 is equal to 1 times 1 plus 9 divided by 2, which is equal to 5. So we have a of 1 is equal to p of 1, and we prove the base case. Then we have our inductive hypothesis. And it's going to be that a of n is equal to p of n. Okay. And then we have our inductive step. Where we want to show that n, a of n plus 1 is equal to p of n plus 1. Okay, so the structure now is similar to what we did in the previous proof. So a is recursive sequence. So we want to express a of n plus 1 as a of n so that we can plug in the hypothesis. And so how do we do that? So a of n plus 1 is equal to a of n plus n plus 1 plus 4. So that follows from this recursive definition. Let me just double check if it is right. Okay, a of n plus 1 is equal to a of n plus 1 plus 4. Great. So we have a of n here. And so we know from our hypothesis that a of n is equal to p of n. We assume that. And so we plug p of n into this. So we get that is equal to p of n. That's n times n plus 9 divided by 2. And then we still have plus n plus 1 plus 4. So that's equal to We have 2 below. We have n times n plus 9 plus 2n plus, what do we have here? 10. That's equal to. So what I want to show is that a of n plus 1 is equal to p of n plus 1. And p of n plus 1 is equal to, this will help us to guide what we're computing now so that we can see into which form we have to put it in. So p of n plus 1 is equal to n plus 1 times n plus 10 over 2. Okay, so let's see if we can get this thing that we started here into this form. So here we have that's equal to, okay, at the bottom we have 2, that's good news. However, at the top we have something kind of weird, not resembling this multiplication. But let's see if we can get it in that form. So at the top we have n squared plus 9n plus 2n plus 10. That's equal to n squared plus 11n plus 10 divided by 2, and that's equal to n plus 1 times n plus 10 divided by 2. Okay, that's it. So we show that a of n plus 1 is equal to p of n plus 1, and we use the hypothesis to do that, and that wraps up this proof by induction. Okay, so those were 3 proofs by induction that I wanted to do as a review, because I think proofs by induction are really important. And now we can move forward. So one thing that I think I already mentioned in the last lecture is the fundamental theorem of arithmetic that you also have in your books. So this theorem says that every integer greater than 1 can be expressed as a product of a list of prime numbers. And here are some examples. 6 is equal to 2 times 3, and so on. So now the question is, what technique can we use to prove this theorem? Well, you can kind of maybe already see just by looking at the statement. So we want to prove something for every integer greater than 1. And so that indicates that maybe we want to use proof by induction. So I'm not going to completely prove this, but I can give you a little bit of a structure. We can assume, if we use proof by induction, that this then holds for all integers up to integer n. So all integers up to integer n can be expressed as the product of a list of prime numbers. And then that's our hypothesis. And we want to prove it for n. So how will we go about this? Well, there are 2 cases then. So either n is a prime number, in which case we're done, because then n can just be expressed at itself, or n is not a prime number, in which case we know from the division theorem that n is then equal to some a times b. And this a and b are both less than n. And then from our hypothesis, if you remember, we assume that all integers up to n can be expressed as products of primes, which means that both a and b can be expressed as products of primes. And then when you put this together, because n is equal to a times b, that also means that n can be expressed as a product of primes. So that's an outline of how you would prove this important theorem of arithmetic using induction. So as you can see, induction is used to prove actual, real important theorems. Okay, so let's now start by introducing our proof by contradiction, which is the main topic of this part of the lecture 6. So if you remember, so for both direct proofs and proofs by contrapositives, or indirect proofs, so far the goal is always to show that there cannot possibly be a counterexample to the proposition. So what is a counterexample? A counterexample is an example that must make, first of all, the hypothesis true. Hypothesis is the left-hand side, and it has to make the conclusion false. And so then to prove, for example, directly that something holds, we want to show that for any element that satisfies A, the same element must satisfy B. If we show that, then we know that there are no counterexamples. However, there is a different type of proof called proof by contradiction, where we assume that we have found a counterexample, and we prove that it cannot be so because it would lead to a contradiction, which is a statement that we know to be false. So basically, we want to show that A and B are logically incompatible. So how do we do proof by contradiction? So if we have a statement of the form if P then Q, first we assume that P and not Q are true. And then starting with this assumption, the goal is to arrive to a contradiction. So what is a contradiction? Here are a couple of examples. If we derive, for example, that P and not P has to hold at the same time, we derive the contradiction. Or if we derive that 1 is equal to 2. Or if we derive that 1 over 2 is an integer, and so on. One common example is that we derive that K is, for example, both an even and an odd number. So these are all examples of contradictions. And so this is a type of an indirect proof. And it's commonly used because it leads to a simpler proof. Okay, so let's do an example. So let's say we want to prove that if n squared is odd, then n is odd as well. And we want to prove it using proof by contradiction. So that means we have to assume, if you remember, that P and not Q holds. So meaning we assume there is an even integer n such that n squared is odd. So n has to be both even and n squared has to be odd. So this is P. And this is not Q. And this is P, and this is Q. Okay, so we assume this, and now we have to derive a contradiction from this assumption. So how do we go about this? So by definition of even and odd, we know that n is equal to 2k for some integer k, and n squared is equal to 2n plus 1 for some integer n. Then, by substitution, n squared is equal to 2k squared is equal to 4k squared is equal to 2n plus 1. From there, if we rearrange things a little bit, we get that 4k squared minus 2m is equal to 2 times 2k squared minus m is equal to 1. And we divide by both sides by 2, we get that 2k squared minus m is equal to 1 over 2. And this is a contradiction, and it's one of the examples of contradiction, because k and m are integers. by closure under multiplication subtraction, 2k squared minus m is also an integer, and hence it cannot possibly be equal to 1 over 2. Therefore, we know that we cannot have a counterexample, which means that the original proposition holds. So this is an example of a proof by contradiction. Okay. Another contradiction example. Proposition is that there are infinitely many prime numbers. Okay, so we'll assume the contrary. So we assume that there are only k prime numbers, p1 to pk, in increasing order. And now we want to derive a contradiction. So let q be their product. That is, q is equal to p1 times p2 times pk. And we also know that q is greater than all of pk's from the property of multiplication. Then let s be q plus 1. So now we know that s has a remainder of 1 for all prime numbers. However, by the fundamental theory of arithmetic, any factor of s can be further factored into prime numbers. But because no prime numbers divide s, because it's remainder of 1 for all prime numbers, we know that s must be a prime number. And this is a contradiction because we assumed that s is not in the original set of prime numbers. And so we know that this cannot be true because this cannot be a counterexample. So that's how we prove the original proposition. Okay, so what has been a great source of confusion in the past is the difference between a proof by contrapositive and a proof by contradiction. So consider this implication, P implies Q. If we do a proof by contrapositive, we want to show that not Q implies not P. And we do so by showing that you cannot have a counterexample to this proposition. If we have a proof by contradiction, we assume P and not Q, and we want to derive a counterexample, a logical inconsistency. Sorry, we want to derive a contradiction, which is a logical inconsistency. So we start by assuming there is a counterexample, and we end up showing that it's impossible. So, that's the difference. So be careful about these differences. So let's show this side by side. If we want to prove if n squared is even, then n is even using both methods. So let's first do proof by contrapositive. So here we want to show the contrapositive of this. So if n is odd, then n squared is odd. So this is our contrapositive, this is what we want to show. And this proof 1 proves exactly this. And therefore it proves the original proposition. In proof 2, we want to start by assuming that P and not Q hold, and then we want to derive a contradiction where P is this left-hand side of this proposition and Q is the right-hand side. So we are assuming that n squared is even and n is odd. Okay, and now by definition we know that n is equal to 2b plus 1 because n is odd. And then from there we know that n squared is equal to 4b squared plus 4b plus 1, meaning that n squared is equal to this, meaning that n squared is equal to 2q plus 1, meaning that n squared is odd. And this is a contradiction with our assumption where we assume that n squared is even. And so we assumed that the counterexample is possible. We reached a contradiction, which means that no counterexamples are possible for this proposition, and therefore we just proved it. So this is an example that illustrates the difference between proof by contradiction and proof by contrapositive. Okay. We talked about this proposition a lot, and we used in the past that every integer is either even or odd. And let's see now how we would prove it. So let's assume the opposite. Let's assume that there is an integer that is neither even nor odd, and let p be the smallest positive integer for which this is true. So we are doing a proof by contradiction. And we want to now reach a contradiction. So, because p is the smallest positive integer that is neither even or odd, then we know that p minus 1 is either even or odd. So in case 1, p minus 1 is even. So by definition, we know that then p minus 1 is equal to 2 times k, and then p is equal to 2k plus 1, which means that p is odd, and that contradicts what we assumed, because we assumed that p is neither even nor odd. So we reach the contradiction. In case 2, p minus 1 is odd, then p is equal to 2k plus 2, which is equal to 2 times k plus 2, which means that p is equal to 2 times n, which means that p is even. And that again contradicts our counter hypothesis, which says that p is neither even nor odd. And so in both cases, we reached a contradiction, which means that our counter hypothesis cannot be true. So there are no counterexamples of this proposition, and hence we proved it. Okay, so that was an example of another proof by contradiction. And this will conclude the part 1 of this lecture. As an exercise, do a couple of proofs by contradiction at home. For example, you can try a similar proof for this just for negative integers. What we did here holds just for positive integers.